Okay, so I've started recording. طيب, let me just remind you of what we talked about last class. And الحقيقة, the topic that we talked about last class is a very important topic because it's a very practical topic that you'll find. Now you carry a mobile phone. I guarantee to you that in your mobile phone, there are at least maybe 3 or 4 or 5 different components that will convert continuous time signals to discrete time signals. There is a component that will convert your voice, which is a continuous time signal, to discrete time signal. Okay? Because your mobile phone only can transmit digital data. Digital data means that the continuous time signals that are represented by your voice need to be converted to digital. Your mobile phone receives electromagnetic signals, okay, which are Bluetooth signals. It receives from the mobile towers. It receives 3G and 4G signals and so on. All of those signals are continuous time signals. But your mobile phone cannot process those signals as they are. So it has to convert them into discrete time. So this is why I'm saying that in your mobile phone alone, you at least have 3 or 4 or maybe even more analog to digital converters, or basically what we call continuous time to discrete time converters. Whenever you have a continuous time signal that you need to process it in a digital device like your mobile phone or your computer or your TV and so on, you always have to convert it into discrete time. And we said that the first step of converting any signal from continuous time to discrete time is what we call sampling. Okay? So sampling is the first step. And we said that there's another step which is called quantization, but quantization, you'll probably study it when you study EE207. It's not our interest now. Okay? Our interest is only the sampling. Now, we said that whenever you sample a signal, you'll always sample it with a specific frequency, omega s, or always sample it with a specific at a specific period, meaning every ts seconds. Okay, you'll go and look at the continuous time signal and pick a value. Right? Ts seconds later, you'll pick another value. Ts seconds later, you'll pick a third value, and so on. Okay? And we know that omega s and ts are related by this formula, which is 2 pi divided by ts. Okay? And we said that one of the ways of thinking of sampling is using that impulse function. The impulse, when you hit it, when you multiply it by any signal, the impulse cancels everywhere of that signal and only leaves the value of that signal at the location of the impulse. This is the thing that we said whenever we multiply any signal by an impulse. And we said that this means that if we multiply our signal x of t by not a single impulse, but by what we call a train of impulses, a sequence of impulses that are separated by ts seconds apart. Meaning we can define a signal that looks like this, which basically contains an infinite number of impulses that come ts seconds apart from each other. And if you plot this, we said this is how it looks like. And so on, and also on the other side, okay, where this is at ts, 2ts, 3ts, and so on, minus ts, minus 2ts. If we multiply our signal x of t by this, everywhere it will become equal to 0, except that at the location of each one of those deltas, I'll have the delta scaled by the value of that function, by x of t. So I'll get impulses that look like this now. The different impulses will be scaled by the height or by the value of that signal. Okay, something like this, where this is x of t. So this is basically what we said. Now, our aim last class was, okay, if we say that x bar is equal to x of t multiplied by this train of impulses, and we know capital X of omega, which we just represented it by this triangle shape. We're just assuming that we have an x of t that has a Fourier transform, which is this capital X of omega, which looks like a triangle. Now, clearly, different signals will not have a Fourier transform or spectrum that looks like a triangle. Some signals will have shapes that look more complicated than this. But the triangle there is just a representation, just something that shows you what happens to the signal. لا أقل ولا أكثر, okay? Don't understand that every signal that we sample will have a spectrum that looks like a triangle. If it was not a triangle, if it was doing something like this, same principle will happen to that signal. Okay? Now we said that if this is capital X of omega, which is the Fourier transform of x of t, which is the Fourier transform of this x of t, then we can find what capital X bar of omega, which is the Fourier transform of this x bar of t. Again, yani from x of t, what is x of t here? X of t, we know that it has a Fourier transform, which is, sorry, capital X of omega. Okay? Now, our intention here is, what is capital X of omega? Where X of omega, I'm sorry, where capital, sorry, let me say it again. We know that X of t has a Fourier transform, which is capital X of omega. The question is, what will the shape of X, capital X bar of omega, which is the Fourier transform of x bar of t, where x bar of t is simply equal to x of t multiplied by that train of impulses. If we multiply any signal by a train of impulses, how does the Fourier transform of that resulting signal look like? And we saw yesterday with a little bit of math, it's not that difficult to show, by the way. You can easily, if you understood the Fourier transform concept, you can easily find what is the Fourier transform of this, and then multiply the Fourier transform by x of t. And you see that once you do this, capital X bar of omega becomes equal to x of omega, and then shifted versions of x of omega to the right and to the left by omega s, where omega s is the sampling frequency. That omega s, remember. What is that omega s that we talked about? This omega s, which is clearly related to the sampling period. Okay? And if you sketch it, if this is capital X of omega, capital X bar of omega will look like this. Okay? Where we have copies, one copy at 0, another copy around omega s, a third copy around 2 omega s, the fourth copy at 3 omega s, and each one of those, by the way, is called an image. Okay? And one at minus omega s, minus 2 omega s, minus 3 omega s, and so on. Okay, fine? So this is basically the last thing, more or less, that we reached. And I remember that at the end of last class, I was trying to reach the following conclusion. Based on this, what is the minimum sampling frequency? What is the minimum value for omega s that will allow us to do this? We were able to get, let me see if I can do this. Let me just give a minute. I'll do something here. Just shrink it and let me. Just give me a minute. Let me do something in here where I'll erase this mess and take a screenshot, print screen, and come and put it in here. Okay. And I'll come in here and do the same thing with this. I just want them to be on top of each other. Okay. And let me take another screenshot. Screen. And let me take this and move it to the back. There. Okay. Now, those are x of omega. This one is x of omega. Let me just make it a little bit bigger. This is x of omega. This is x bar of omega. So when we sampled this, when we multiplied it by the train of impulses, this is what we got. The question now is, how do you go backwards? And I remember I asked yesterday, and one of you was accurate in saying that to be able to go from x bar of omega, let's say that now we have a sample signal, a signal that contains those train of impulses that are scaled by x of t, which will have a spectrum that looks like this. How do we go back to the original signal? And the answer is quite simple. clearly this signal, this is only one copy, one image of the signal that we have below. The signal that we have below contains infinite number of those images. We are only interested in the one that is located at 0. So if we put a low-pass filter, something like this, in here, and low-pass filter always go from 0 to some frequency in here. I'll call it, for example, omega LP, low-pass. Okay, the frequency, the bandwidth of the low-pass filter. If we put a filter in there that has a specific frequency, specific bandwidth, we will be able to extract only the middle one and cancel all of those. This is basically what the low-pass filter will do. Now, I remember one of you asked me yesterday, but this is scaled. This is A over Ts, and this is A. Yes, he's absolutely right. What if I made this filter what they usually call it an active filter? What's the difference between a passive filter and active filter? A passive filter only contains capacitors, inductors, and resistors. An active filter, in addition to having capacitors, inductors, and resistors, it also has amplifiers. What if I made the magnitude of this be equal to Ts, whatever Ts is? Which means that the signal, when it passes through that filter, it will be multiplied by a value that is equal to Ts, whatever Ts is. If Ts is equal to 10 seconds, it will be equal to 10 seconds. If Ts is equal to 0.1, it will be multiplied by 0.1. Okay? So if I multiply this signal, in addition to filtering it, by a filter that has a magnitude, not a magnitude that is equal to 1, but a magnitude that is equal to Ts, the Ts will cancel with the Ts there, and I'll end up with exactly the same input. Okay? Now, clearly, if we put a low-pass filter, theoretically, we should be able to go from the sample signal back to the original signal. I assume that you understand this concept. Now, my question to you yesterday, and this was the point at which I stopped, was the following. What is the requirement that I must have when I sample the signal, when going from here to there? I must have done, or let me say this way. I think someone told you that I have this signal, and I want to sample it. Okay? I want you to choose all of the parameters of the sampling. What are some of the parameters of the sampling? What is the sampling period? What is the sampling frequency? Maybe what else? More or less, those are the things that you need to select. Okay, maybe select, for example, the sampling frequency. What is the sampling frequency that you need to select so that when you go from this upper signal in here, from this yellow one, when you go down to the orange one, I will be able to put a low-pass filter there to be able to extract back this original signal without any distortion. If you select a sampling frequency that does not satisfy a specific condition, you'll see that going from top to bottom will be okay. I mean, you're not going to, no problems will appear when you go from the original signal from x of omega to capital X bar of omega. You're not going to see any problem. But when you try to go back, when you try to do the opposite direction process, a problem will happen that will cause let's say the signal, the signal that you get, what they call the reconstructed signal, to be a distorted form of the original signal. Basically, the signal that you'll get in here when you go back, okay, will not be the same as the signal. It will be different. What is the condition that you have to satisfy for you to be able to sample and be able to reconstruct or get back the original signal without any distortion? Anybody can spot that feature or that requirement. If you have an answer, just speak, because I don't have. I cannot see who's.
Doctor, I think it's two conditions. Okay. The first condition is the distance should be B, bigger than B for the copies. And the other requirement is the filter has to be to the nth order required to not include the copies.
Okay, thank you so much. You're very close with the first one. The second one I understand, and you're right. Okay, the first one is not exactly right. What is you said bigger than B? What is bigger than B?
WS omega S minus B from the height.
Oh yes, exactly. Yes, you're absolutely right now. Okay, then both of your two conditions are right. Okay, basically, gentlemen, what your friend said is this. Look, we will only be able to put a filter in here to extract the original image, the lower frequency image, the image around 0 frequency, okay, if we sample so that this image does not overlap with this image. They do not overlap with each other. They do not occupy the same frequency. Not even part of one of them will overlap with part of the other one. Okay? Meaning they must be separated. You see in here, there is a separation between the two. How much is this separation? It's the distance between omega S minus B. Notice that this is omega S. Omega S is always the center frequency of each one of those images. Omega S or 2 omega S or 3 omega S and so on. Okay? So this one is located at 0. This one is centered around omega S, which means that if this duration is B, or if this distance is B, this distance is also B, which means that this frequency is equal to omega S minus B. I want to make sure that omega S minus B is greater than B. So I want omega S, you write it this way, minus B has to be greater than minimum value. The minimum is that it has to be equal to B, which is the bandwidth of that signal, the signal that I'm sampling. Okay, which means that omega S has to be greater than or equal to, take this minus B to the other side, equal to 2B. Okay, the minimum frequency that you should use, in radians per second in here, is that the minimum sampling frequency has to be equal to double the bandwidth of your signal. If your signal has a bandwidth which is equal to 2 pi times 1,000 hertz, 2 pi 1,000 radians per second, then you have to sample at 2 pi times 2 times 1,000 radians per second. If you sample at a frequency that is greater, that's okay. This means that the images will become further away from each other. If you sample at a frequency that is lower than this, if you decided to sample, for example, at omega S, assume that 2B, by the way, this is if we use, sometimes I like to write it in terms of if rather than omega S. Okay? Clearly, if omega S is equal, for example, to 2 pi, or let's say 2B is equal to 2 pi times 2, which is this 2 in here, times 1,000, which means that the bandwidth of your signal is 1,000 hertz. Right? Which means that you have to sample now at a frequency which is equal to 4 pi times 1,000. So your omega S has to be greater than or equal to 4, I wrote it correctly, 4 pi times 1,000. Okay? Which means that if S, the sampling frequency in hertz, has to be greater than or equal to 2,000. I started with a signal that has a bandwidth of 1,000 hertz. So I need to sample at 2,000 samples per second, or 2 pi times 2,000 radians per second. Okay? If you do this, those two images, the worst case is that they will touch each other, and you'll get something that looks like this. They just touch each other. Now, if they touch each other, theoretically, you can still separate them from each other. You can just put a filter in here that looks like this. And this was the second point that your friend made. Okay? If you put a filter like this, you'll be able to separate them. You'll be able to extract this and reject this and every one of the other images. The problem with putting them side by side, touching each other, this means that you have to use a filter which is very sharp. It has a transition region. This is called the transition. It has to have what they call a sharp transition, a transition which is just a line, a vertical line. The problem with filters that have a transition which is vertical like this is that they have to have an infinite order. You cannot build a filter like this in reality. All filters that you can build will always have a transfer function that looks like this. Typically, it is smooth. So you want to make sure that in the transition region in here, in which you are going from the pass band, you remember when we talked about filters, we said that this is called the pass band. This is called the stop band. Okay, and this is called the transition band. Transition band. Okay, you need always to make sure that your image that you want is in the pass band, and all of the other images that you don't want are in the stop band. This is a practical filter that you can build. This filter is not practical, you cannot build. So if you make them touching each other right away, this means you have to use an ideal filter, basically. And ideal filters do not exist. Okay? Which means that if you use now a low-pass filter, and let's say a real low-pass filter, if they are touching each other, what you'll have to do is you'll have to do something like this. Okay? Which will kind of distort a little bit of your image that you want and let part of the image that you don't want pass. And this is some form of distortion. You'll hear the signal, but it will be slightly distorted. So what do they usually do? Whenever they want to sample, they don't sample at exactly 2B. They sample at slightly higher, maybe 10%, 20% more than this. So instead of, for example, 1,000 hertz, meaning that you need 2,000 samples per second, they sample maybe at 2,500 samples per second. And the idea there is to keep a gap between the different images. You keep a gap in there that will allow you to put a filter that is a real filter, something like this. In here, and something like this. Yeah, that's why you remember when I mentioned human voice, I said that human voice has a bandwidth that is equal to approximately 3,500 hertz. Typically, I know that there are some people who probably have frequencies that are higher than 3,500, like probably females. Not only that, there are some people who have kind of, I don't know, soft voice. Their voices, something like this, high frequency. Right? While there are people who have low frequencies. Their voice is kind of low frequency. Anyway, the average, let's say, bandwidth of a human voice is roughly speaking 3,500. That's why you need minimum of 7,000 samples per second or hertz. Sampling frequency that is equal to 7,000 samples per second to sample. Typically, the standard is you go with 8,000. Okay? So this is why 8,000 is kind of the standard. If you decided to use, for example, 50,000 or 100,000, is that bad? Well, it's not necessarily bad. It's just that the high sampling rate there will generate for you a lot of data that you need to transmit. If you need to transmit this data or you need to store this data, okay, then the higher sampling rate that you have, the bigger your file is going to be. That's exactly like, let me just put things in perspective. If, for example, you're taking a picture of a document, for example, or let's say you're scanning a document. Right? Sometimes you see, for example, that if you use a resolution of the picture of 1,000 by 1,000, that's enough. Should you take 1,000 by 1,000, by the way, is 1 megapixel. Right? Should you use, for example, now some cameras in mobile phones are 48 megapixels. Some of them are probably even higher than this. I don't know. Right? Should you use a 48 megapixel to store an image in which you can scan it, or let's say using 1 megapixel? Now, you can always do this, but what's the cost? The file size is going to be maybe 10 times or 15 times the size of the original file. Okay? So clearly, you're going to get better quality, but what's the cost? Storage of the data becomes larger. If you want to send that file, instead of taking, for example, 20 seconds, now it's going to take maybe 5 minutes, especially if you have a slow internet connection. Okay? So there's always a compromise. If you sample at a low frequency, the quality may deteriorate, okay? But the good thing is that transmission of the data or storing of the data does not take that much effort to do. If you sample at very high sampling rates, the quality becomes super good, okay? But the cost is, or let's say the drawback is that storing or transmitting that data requires significantly more effort to do. Okay, gentlemen? That's why almost always, if I ask you to sample, if for example you ask me to sample a signal, I'll tell you what signal are you talking about. If you tell me it's human voice, I'll tell you I'll sample it at 8,000 hertz. Now, can you use 8,000 hertz to transmit music, for example? Is it good? This is basically what I'm asking you.
No, definitely not.
Why not? Why not?
Because music has like all ranges of frequencies. It has higher ranges of frequencies.
Yes, absolutely. Yes, yes. Okay. In fact, human voice cannot produce the same frequencies that some of those, I don't know, musical instruments produce. Okay. Now, no matter how soft I make my voice, okay, probably the frequency is maybe 3,000 hertz, or I don't know how much. Okay. By the way, I have a tool in my mobile phone. I don't know if I don't think that I showed it to you. Okay. I have a tool which is called. By the way, I have an Android-based mobile phone. Okay. And the tool, I like that tool, الحقيقة. And sometimes I use it. What is the tool called? Yeah, it's called Spectroid. Right? If you have an Android, maybe it exists for the iPhone. It's called Spectroid, which is a very simple tool. It's probably less than 1 megabyte or so. Right? But the good thing about it, in fact, let me show it to you. Right? I don't know if I can turn on the camera. I'm not sure if you'll see it or not clearly. I forgot how to turn on the camera. Okay. Yes, let me turn on the camera. I don't know if you can see it. Just give me a minute. Is the camera on? Or no, not on. Okay. Share. Do you see me now, gentlemen? Okay, I think you see me. Okay. This is basically the tool.
You can see.
Okay. Now, I'm not sure you see it clearly or not, but basically this is the tool. And you see, as I speak, I'm sure that you're seeing that there's fluctuation in the signal. Let me just stay quiet for a few seconds. Okay. Now, this is the noise, by the way. There's a small fan that is cooling my computer, so it's producing a little bit of noise. Let me just turn it off, just to show you. Okay. So anyway, yeah. Now you see, I'll try to produce a little bit of high frequency. I don't know if I will be successful or not. Okay. I don't. Let me see. I don't know what frequency it was showing. By the way, it was showing you. So my apologies. It was showing you something that was kind of compressed. So I'll show it to you again. I'll show it to you again. Okay, I'll show it to you again. What is the frequency? Probably, maybe it was 1,000, 2,000, I don't know, something like this, okay? You know, what I'm trying to say, is, gentlemen, is that human voice, no matter how hard you try, is not going to be more than maybe 3,000, 4,000, 5,000. I'm sure that you've heard of some people who can sometimes break a glass by producing high frequency. Those are kind of superhumans, by the way. Not everybody can produce that high frequency that will break a case or glass for you. But there are apparently some people who can do this. Music can produce sometimes frequencies that reach 12,000, 13,000, 14,000, and so on. This is why if you wanted to transmit or you wanted to store, let's say, good quality music, you should not use your mobile phone. Yeah, never record music just like it is a voice. Why? Because voice has a frequency which is equal to maximum of 4,000 hertz, as I mentioned. So when you sample it at 8,000, that's enough. But if if music, for example, produces a frequency of, for example, 15,000, then the minimum frequency that you need to sample it is approximately 30,000. Now, the human ear can hear frequencies up to approximately 20,000. And music, by the way, sometimes can produce frequencies very close to 20,000. Now, there are, by the way, some tests that will allow you to tell how good is your ear. And I remember that, in fact, you're probably going to think that I'm a geek now. I have also another tool that produces to me different frequencies. Now, this tool that I just showed you, allows me to see the different frequencies that I am, let's say that are around me. I have another tool that generates for me sinusoids with different frequencies. And you can just change the frequency there as you wish. And you can hear those frequencies and you can tell how good your ear is. Last time I did it, I think I was able to hear up to about 14,000. Okay? Now I'm relatively speaking old. With age, higher frequencies, the ear starts to lose those frequencies, the higher frequencies. I tried it with some of my kids, with one of my kids, okay, I think the middle kid, okay, and he was able to hear, according to him, up to 16 or 17,000 hertz. And I was continuously increasing the frequency, and I told him that when you don't hear anything, let me know. And I think he said around 16 to 70,000 hertz, he was able to hear something. Okay? Now, clearly, if you want to sample music, you should not sample it with the same sampling frequency of the voice. The quality that you'll get at the other end, whether you're going to store that signal or transmit it, is going to be a very bad quality. Okay? In fact, it's going to be not only bad, it's going to be terrible. Okay? It's going to be something like someone is sitting in a barrel. Okay? I don't know if you have ever experienced this. If you are sitting in a place where it's kind of confined place, okay, and you speak and someone outside that place is listening to you, okay, he hears your voice like this. It might even be worse than this. Okay? So clearly, if you want to record music or you want to transmit music, you need to sample it at much higher frequency. Typically, for music, they use something like 44,000 hertz. So for music, they use 44,000, which means that roughly speaking, frequencies up to approximately 20,000 hertz will be stored for you. All good quality music will use this frequency. Now, again, what is the cost? The cost is significantly increased amount of data that you need to transmit compared to 8,000. Okay, Juan? Right. Now, what happens if I thought this? I don't care. I have a signal which is music, okay, which has this frequency, but I will go and sample it with this frequency. So I have 20,000 hertz. My signal is 20,000 hertz, but I will sample it at a frequency that is equal to 8,000 hertz. What will happen? You may think, so what? Will music, for example, complain? No, clearly music is not going to complain. But what you will hear at the other end is going to be a mess. And something is going to happen that you probably never thought about in the past. I'm sure all of you have seen this thing, but you never attributed it to this phenomena that I'm going to talk about in a minute. Okay? What will happen if you have a signal? Sorry, I went down. Yeah. Okay. What will happen if you sample a signal? What will happen if you have a signal? Let's say that, like, I don't know, for some reason my computer is sometimes freezing. Okay. What will happen if you sample at lower than the double the? By the way, that sampling frequency, the double the frequency, is called the Nyquist rate, Nyquist sampling rate. Nyquist is a scientist who worked on. In fact, he's the one who put all of those theory. The theory of the minimum sampling rate for you to be able to reconstruct, to get back your signal without distortion. It was that scientist who was called Nyquist. I think he lived in the beginning of the 20th century or so. Okay, anyway, he is the one who put the theory for this sampling rate, which is basically called the Nyquist sampling rate. And he basically indicated that if you have a signal and you sample it at a frequency which is lower than double the bandwidth, okay, where omega s is less than 2 times the bandwidth, then the different images will overlap. Now, because of that overlap that I'm showing in here in black, you will have, you'll say either I will filter in here, something like this. Let me make a different color. Either I'll use a filter that is this wide to pass my image that is at 0. But the problem of doing this is that you're allowing a significant part of the adjacent image, which is this part that I've shaded in here. Or let me shade it in a different color. you are allowing part in here that I am yellow. You are allowing all of this yellow part in here to pass from here and from there to pass. Okay, this is significant amount of distortion. It's true that you're getting your whole signal inside, but you are allowing, relatively speaking, large part of the adjacent images to also be produced at the output. By the way, I'm assuming here I'm using an ideal filter. If you're not even using an ideal filter, the situation becomes worse, because now your filter looks like this. So let me use red. Your filter is like this. So it's distorting your image that is in the middle and allowing significant amount of adjacent images to pass. So even assuming that we have an ideal filter, you're already getting distortion, not because of not using an ideal filter. You're using an ideal filter, but because the adjacent images, part of them is overlapping the image that is at 0. Okay. So one option is to filter using this bandwidth here, or let's say a filter with this bandwidth. Another option is to say, well, let me remove all of this distortion by using a filter like this. But now, what's the cost? It's true that you have removed all of this distortion from adjacent images. You have cut part of your signal. Part of the signal that you want, which is this part in here, is lost. See this part in here? The one that is I'm coloring in yellow? You have completely eliminated this part. So again, you're getting a signal at the output, which is distorted version of your input signal. Usually, typically, what they do is, if you have a situation like this, they'll use a filter which is basically in the middle here. So you are losing, sorry, not in here, you are losing part of your signal and allowing a small part of the adjacent images. Typically, this is what they do. Okay, so you are losing this part in here, and this part in there, and you are allowing this part in here, and this part in there. The blue you're allowing from the adjacent images, and the yellow you are losing from your image, from the image that you want. So it's something in between. Typically, this is what they do. Okay. Now this has significant, let's say, what's the appropriate term that I should use? It has a significant, well, I don't know, I don't have an appropriate word for saying it, but it appears, whenever this situation happens, it appears as something that is completely weird. Whether you're talking about sampling sound or taking pictures using video. By the way, you know that video, if you're taking pictures, let's say if you're using your mobile phone to take pictures of something that moves, you know that your mobile phone is actually taking pictures one after the other. This is basically the difference between a picture and video, is that a picture is just one picture, and that's it. Video is 30 frames per second or 60 frames per second, or maybe now there are some cameras and some mobile phones that can take pictures, something like 120 pictures every second or so. Very high resolution. Those are the cameras that can record, or the mobile phones that can record in slow motion, where you do recording of, for example, 3 seconds and then expand it to 10 seconds or 20 seconds. Right? How do they do it? They just take high frame rates. They take pictures at a higher frame rate than usual. The standard frame rate for video is 30. Now, many TVs and many computer screens and so on have a frame rate of 60, and now even some of the high-end monitors and so on have frame rates of about 30, 120. I'm sorry. Okay. Now, what's the effect if you take pictures of something that change very fast? I'll tell you something now that you probably never thought of. Have you ever looked at the wheels of a car or anything that rotates? Okay, as it is spinning, what do you notice? Assume that you have a fan, for example, مروحة, okay, that is spinning, and it was off and it starts spinning. You notice something. I'm sure, I guarantee to you that all of you have noticed this without an exception, and you probably never thought about it. You never thought, why does it, or let me maybe correct myself. You probably thought Why does this happen? But you were never able to figure out why it happens. What happens when you're looking at a fan and you turn it on? As it starts speeding up, what happens to it? Anybody can comment on what happens to anything that rotates? Yes, please, just speak, one of you.
Kind of stop the spinning, Doctor.
Yes, and it stops spinning. What happens after that? Yes, two things will happen. Yes, certainly. Blurring will happen. Okay, and I'll explain to you why blurring will happen. Okay, but blurring is not really the issue that I'm interested in. I'm sure that all of you have noticed that when you have a fan and you keep looking at it as it is speeding up, you notice that it's speeding up, speeding up, speeding up, and then at a specific speed, it appears as if it is slowing down.
Yes.
Slowing down, slowing down, slowing down, until at a specific speed, it appears that a fuzzy version of that fan, as if it has stopped. And then it starts spinning again in the same direction. Faster, 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 faster. And the same thing happens again and again and again. Maybe for 4 or 5 or 6 times sometimes. I'm sure all of you have noticed this. Do you know what this is caused, or what causes this? It's exactly this phenomena. By the way, this phenomenon is called aliasing. And I'll explain it to you, and I'm sure that once you understand it, you'll never forget it. It's called aliasing. And it happens in many phenomena, not only in fans, but in many phenomena, and I'll give you maybe also some flavors of things that you've probably seen, but you never was able to explain. I'll just say, I think it is worth mentioning this, although I'm kind of maybe tight in time, but it's okay. I'll mention it. Okay. Assume you have a fan that only has one blade. Now, clearly, you cannot have a fan that has only one blade. But I think it's simpler if I think of a fan that only has one blade. Always fans will have either 2 blades or 3 or 4 and so on, and they are scattered so that they become balanced. So that, if you have a fan that looks like this, clearly it's gonna vibrate. But let's say, forget about vibration. Assume that the fan does not vibrate. Do you know that the human eye acts or works just like a camera? And it takes, roughly speaking, 25 or 24, I don't know the exact number, but the typical human eye will take, roughly speaking, 24 pictures per second. The human eye, your eye, my eye, and so on, the typical human eye, there are probably some people whose eye is maybe a little bit better, some people who have eyes that are a little bit worse, but the standard eye of a human being will take pictures. It behaves as if it is a digital camera, believe it or not. Yani the flow of signals from your eye to your brain happen, roughly speaking, at a rate in which it appears that your eye is taking pictures or frames at a rate of approximately 24 or 25 samples per second. Just for the sake of argument, I'll say that you're taking pictures every 1 second per one picture per second, just for simplicity. Okay, so assume that your eye takes pictures 1 picture per second. Now, as this starts rotating, and assume that it takes, for example, 10 seconds for it to make one complete rotation. So the first picture, what happens? This is the image that you'll get, right? So let's say this is time. Let me do it this way. Let me put the fan in here, and let me put time in here. 1 second, 2 seconds, 3 seconds, 4 seconds. And please pay attention to this. Yeah, honestly, if this is the only thing that you get from this topic, I think it's worth it. At least you'll be able to explain it when you see it next time. You say, this is the early thing that what you talked about in the course. 4, 5 seconds, 6 seconds, 7, 8. I'll just reach 10, 9, 10, maybe 11. Okay. Assume that the rotation here rotation speed is equal to 1/10 of a second. Okay, meaning it. Let's say, I mean the rotation period, not the rotation speed. rotation period is equal to 10 seconds. Sorry, 10 seconds. Okay, which means that the frequency is 1 over 10. Yani every 10 seconds it makes one complete rotation. So the next second your eye takes a picture, where will the fan be? And assume that I'm rotating clockwise. So the fan will be a little bit tilted there. The third one, a little bit tilted. Fourth one, something like this. Sorry, maybe my plus are not really good. Sorry, the fifth one will be down. Sorry, I need maybe to be a little bit more accurate. 2, 3 will be 0. Okay, let me start with 0. My apologies for this. I think it makes sense to start from 0. 0. Let me erase all of those. Yeah, what was confusing me is the 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. Okay. So at 1, at 0 it was on top. At 1 it will be somewhere there. At 2 it will be somewhere there. At 3 it will be somewhere there. At 4 it will be somewhere there. And at 5 it will be exactly the opposite, because it takes 10 seconds to make one complete rotation. So clearly after 5 seconds it will be in the opposite direction, pointing down. 6, 7, 8, 9. Okay. And at 10 it will return to exactly its same location, right? Now your eye طبعا takes pictures, and your brain analyzes those pictures and sees, it was here, then it went a little bit there, and then it went a little bit there, there. So your brain is thinking, clearly it is rotating clockwise, because it's seeing it move slowly from one picture to the other. Okay? Right. Now let's say that you started speeding up the rotation speed. And instead of being 10 seconds, assume that you made it now 3 seconds or 4 seconds. Let's say. Yeah? Assume that you made it 4 seconds. So now it's speeding up. So now the frequency is 1 over 4. It was 1 over 10. Now it's 1 over 4, a quarter, instead of 1/10. So now in the first picture, it will be up. Second picture, it will be 90 degrees. Third picture, it will be down. Fourth picture, it will be here. Okay. After 4 seconds, it will be up again. Again, your brain is interpreting, it's seeing it 90 degrees, and so on. Your brain is going to interpret it this, by the way, the direction of rotation. Your brain is going to interpret it that, again, it's rotating clockwise. Now, let me go to the case where the period is equal to 2 seconds. Now, it's speeding up, so now the period is equal to 2 seconds. What will happen in this situation? In the first picture, it's pointing up. In the second picture, it will be pointing down. Okay. In the next picture, it will be pointing up. Next picture will be pointing down, and so on. At that speed, by the way, your brain is not going to be able to tell, is it clockwise or counterclockwise? To it, the human brain always interprets the shortest distance, let's say, between the objects that it sees, that this is the direction of rotation. Now it is completely flipping, one time above and one time below. Okay? So your brain at that point is going to get confused. It's not going to be able to tell whether it is rotating clockwise or counterclockwise. Now the fun thing will happen is if it starts rotating a little bit faster, let's say 1.5 seconds. Do you know what will happen now? In the first picture, it will be pointing up. In the second picture, it's not going to be pointing down. It will be pointing a little bit further away, because now it takes only 1.5 seconds to make one complete rotation. So the next time your eye takes a picture, this is the location of the blade of the fan. The next time it will look even that it has rotated somewhere in there. You can do the math and you'll see that it will appear like this. Hold on, let me see. No, sorry. Okay, let me take the situation in which it's 1.1, just slightly. The period is just above 1 second. Okay, so each second it did not make one complete rotation. It's just missing approximately 5 degrees or 10 degrees, something like this. Okay, now the next picture. So this is at 0. The next picture, it will be just shy of making one complete rotation. The next picture will be just shy of making 2 complete rotations. The next picture will be just shy of making 3 complete rotations, and so on. Do you know what your brain will think now in this situation? It will think that it is rotating in the other direction. And this is exactly what happens. Because your eye is taking pictures at a finite rate, which is equal to 24 frames per second, roughly speaking. So anything that rotates at a speed that is close to 12 or 13 or so, clearly if you have more blades, the phenomena there will appear more frequently. If you have only a single blade, it will become, let's say, less apparent for you. If you have more than one blade, if you have 10 blades or 20 blades in the fan, like for example, an airplane engine, this phenomenon will appear even significantly more, because now each blade will come in place of the other blades. You can do the math. If you analyze it for a fan that contains 2 blades or 3 blades, you'll understand what I'm talking about. Okay, but basically this phenomenon, gentlemen, appears whenever you have anything that samples something that rotates. You'll always see this phenomenon. You also see it in car wheels, for example. If you're looking at a car that's speeding up, or let's say a car that is traveling on a highway, and someone is holding his camera and recording the wheels of that car, you'll also see it. Why? Because the camera itself takes pictures, just like your eye. Right? So you understand now this phenomena? This phenomena is called aliasing. Now, how does it appear? In I think I have about 5 minutes. I think it's enough at least to explain this. How does it appear? Or why does it appear? For example, how does it appear if you're talking about sounds? And maybe if I have time, maybe I'll develop for you a simple application, simple MATLAB application, and let you run it. And I'll show you that if you sample a signal at a low sampling rate, relatively speaking, high frequency signal, you sample it at low sampling rate, this is what will happen. Let's say that we took a signal in here. You see the signal in here, x of omega. Assume that it was not like this, it was just a cosine. And we have learned that if we have a cosine, gentlemen, what is the spectrum of the cosine? How does it look like? It looks like this. 2 impulses, one at omega, let's say omega x, and one at omega 0 and minus omega 0. Cosine, let's say. Okay? So if you have a cosine, this is the spectrum of a cosine. Let's say that we sample this cosine at a frequency that is much greater than double omega 0. How will the sample signal look like? It will look like this. This is one image. This is another image. This is a third image. This is a fourth image, and so on. Okay. So now I can bring a low-pass filter here, and I can extract this filter, and I can extract the original image, and I'll get exactly the same signal. What happens if I reduce the sampling rate or increase the frequency here of this cosine? This is what will happen. Let's say that I reduce the sampling frequency. If I reduce the sampling frequency, those images will come closer to each other. This will come closer. This will even come closer, and so on. Eventually, if you keep reducing the frequency, this thing in here will come at a frequency that is lower than the frequency of this. You see this thing here? Okay. The frequency of this will come. For example, this is omega s. This is omega s minus b, and this is b. Let's say that you made omega s minus b. I'll just give you numbers there. I think it's easier. Assume that this is 1,000 hertz. And in here, I sampled at 10,000 hertz. Okay? So this becomes equal to 9,000. What if I reduce this 10,000, reduce it to exactly 2,000? Okay? If you reduce this to 2,000, the location of this impulse now becomes exactly at 1,000, which means that this overlaps with this one. Those two will overlap with each other. They become on top of each other at 1,000. Now, if you extract this, it will appear to you that everything is okay. But let me reduce the frequency a little bit more. If you reduce the frequency here, the sampling frequency from 2,000 to 1,500. Okay, this frequency here becomes equal to 500. It's b less than the sampling frequency, which is 1,500. So it becomes at 500, which means that this impulse in here will come somewhere in there. It will come at 500. So in fact, if you do this, if you sample a signal that has a frequency of 1,000 hertz at only 1,500 hertz, and then you extract, if you put a filter, for example, with a frequency that is equal to 1,100 hertz, you will hear, believe it or not, you will hear another signal with a frequency that is equal to 500 hertz that you think, where did this signal come from? What did this signal come from? It came from the adjacent image because of that fact, which is called aliasing. Aliasing basically is when the different images overlap with each other. Yani basically this black thing in here, where's the image? This black thing in here is called aliasing. Okay? So aliasing is the overlap of adjacent images of sample signals. When you sample at a sampling frequency that is less than the Nyquist rate. Okay? I'll just mention this and I'll leave it to you. There's also another phenomena. I don't know if you have ever seen it. عارفين هذا ايش يسمونه? You know this screen that sometimes is put on windows to prevent insects from coming into the house. I want you to do this. If you have any of those of this screen at home, take a piece of it. This screen that looks like this. Okay, something like this. The one that they put on windows. Okay, take a piece of it, cut it, something like, I don't know, 30 centimeters by 30 centimeters or 40 centimeters by 40 centimeters. Cut two pieces and put them on top of each other, such that they are not perfectly aligned. Something like this. If you do this, you see regions of black and regions of white, or let's say, you see regions that have kind of dark and regions that are not dark. This is exactly the same phenomenon. This is also called aliasing. Think of the screen as sampling what's behind it. The screen, what is the screen? It's little small squares. Okay, so as if it is sampling the image that is behind it. If you put another screen on top of it, yeah, it's like sampling the sample signal. And when you sample two signals at a rate that is not exactly the same, you end up with, again, aliasing. It happens in a lot of phenomena. The most notable ones are, as I mentioned, this one, as well as a disk or anything, let's say a fan that keeps rotating, you see it as if it is speeding up and slowing down. Okay? So anyway, I'll stop at this point. Inshallah, I'll meet you tomorrow.